name is Brahim Lemirboua. I'm from Ibn Saud University, Agadir, Morocco. Thank you for giving me the opportunity today to present to you my work. The subject of my presentation today is about multi-niche crowding genetic algorithm parameter tuning for molecular potential energy surface computation. It's a bit different of what the valuable presentations we've seen so far. So it's a different field. So the outline of this presentation is as follows. We're gonna start with a little bit of background, and we're gonna present the objective, and we talk about genetic algorithm parameter optimization, the methodology and the results and discussions, and then we're gonna sum up with the conclusions. So to give a little bit of background for this work, it's all about the genetic algorithm. As you can see in the title, it's basically a search algorithm. Genetic algorithms are part of more general algorithms called evolutionary algorithms, which are inspired by evolution theory. To solve different kind of problems. In its simple form, genetic algorithm is mainly used to find the most optimal solution, which can be the global minimum or the global maximum. For more advanced uses, for more complex search problems, more general type of algorithms called multiniche, multimodal genetic algorithm are used to locate, in addition of the global solution, more local optimums in the search space. So what is the potential energy surface? It's basically a representation of the energy of the molecule as a function of its degrees of freedom. As you can see in this figure, we can see a simpler representation of this surface for simple molecules that have only 2 degrees of freedom. We can see that the surface have a global minimum and many local minimum. In more complex molecules that may have more degrees of freedom, the surface is quite complex and hard to represent unless we use some projections use some projections in some other spaces. So in previous studies, we have used an algorithm called multi-niche crowding genetic algorithm, which is basically a type of multimodal genetic algorithms to describe the PES of natural and protonated glycine, and also for different more complex molecular systems. In those studies, the algorithm showed that it's capable to locate all the minimum for those molecules in the PES, but in some cases we observed that the niche count were quite low. The niche count is basically the number of conformers belonging to the same niche corresponding to any given minima in the search space. So that inspired us to look for a way to optimize the algorithm to increase its efficiency for this special use of PES calculation. So the objective of this study is to improve the niche count for each minima and find the best parameters of this algorithm for this special case of PES calculation. And also, we wanted to find out how the size of the molecules is related to the variations of these parameters. So let's talk a little bit about parameter optimization. In genetic algorithms, in general, they have some parameters that need to set up to make it work, like population size, crossover probability, and mutation probability. For the multi-niche crowding genetic algorithm, it has more parameters. We're gonna see them later in this presentation. So for the parameter optimization, there are mainly 2 techniques that are used for this: parameter control and parameter tuning. These 2 type of approaches that we can use. In this study, we use the parameter tuning. Among those parameter tuning techniques, we have used the metagenetic algorithm approach, which is basically using a second layer of genetic algorithm in order to optimize the parameters of the underlying one. So in this study, we used the second layer of the same algorithm. So the benefit of this is not only find one best parameter set, but possibly more than one combination of parameters for a better performance. In this table, we can see the molecules we used in this study. So these are molecules of different sizes. You can see the degrees of freedom of each molecule. The degree of freedom reflects the size of the molecule itself. So the more the molecule has degrees of freedom, the larger is. So this is mandatory to see how the size of the molecule is related to the parameter change. In this table, we can see all the parameters involved in this algorithm. For the ones that have a fixed value, we didn't optimize them for several reasons. If you want to find out more about those reasons, you can refer to the paper we published about this. So we optimize only 4 of them, which we believe are the most important ones in this algorithm. Mainly the first 2 are a crowd-in selection size and crowd-in size, which are used in the selection phase and in the replacement phase. The last 2 parameters, interval crossover and mutation probability, are used in the genetic operation phase. So about the fitness function, we have used the fitness function as follows. So to decide which algorithm is better, the one that have higher number of niches, and in case of equality, especially in the replacement phase, we use a second criteria, which is higher energy average. So the higher among the niches, so that indicates that the algorithm is capable to locate more unstable conformations of the molecule, which makes it more efficient in this special case of PES calculation. So the flow of execution of the algorithm, you can see it in this diagram. We can see that the metagenetic algorithm operates in a population of underlying multiniche crowd-in genetic algorithm. In this diagram, we can see all the steps involved in this process with the fitness function here. So as for the result, we have found for each molecule more than one combination of parameters that lead to higher performance of the algorithm, except for the phenylglycine, which has one more parameter set. For the variation of those parameters as a function of the degree of freedom, we have found that 3 of them have the same trend variation, except for the crowd-in selection size, which has the opposite variation. So as for the conclusion of this study, for the selection phase, smaller molecules require lower values of crowd-in selection size, and larger molecules require higher values of this parameter. For the genetic operations, crossover and mutation, it's quite the opposite for the parameters interval crossover and probability of mutation. For the replacement phase, it's the same as the genetic operations, the same variation. So the main finding of this study was that crowd-in selection size and the probability of mutation needs to be balanced in order to control the degree of exploration of the search space in order to avoid some problems in the algorithms like the premature convergence or the slow convergence, for example. Those trends, just keep in mind that they give guidance for the choice of the parameters for a given type of molecule as part of a combination. So we have to choose all the parameters as a combination, not only one parameter at once. So that's it for me. If you want to read more about this, you can refer to the article we published in this journal for more details about this one. Thank you very much. If you have any questions, you are welcome to.
Thank you, Mr. Brandon,
Brahim.
for your wonderful presentation. Just wanted to know, like very new to genetic algorithm. I'm from not from genetic algorithm background. Just wanted to know, what is the significance of this research, or this field. Basically, how will it be, useful with respect to products or the applications, engineering applications?
Yes, actually, it's all about the theoretical chemistry. We use some programs to look for structures of molecules. In previous studies, we used this algorithm to find those structures, more stable structures for some molecules. In this study, we studied the optimization of the algorithm, so we can choose more optimal parameters of the algorithm in order to find more structures, stable structures for any molecule we can study with this system.
What is the traditional approach and the present approach differences with respect to selecting any molecules or anything? What is the traditional and the convention or the modern genetic algorithm way differences?
Actually, any algorithm has a default setup. The conceptor of the algorithm provided some guidance, general guidance for the choice of those parameters, but it depends on the problem you can study. In this special case, we found that the algorithm might need some fine-tuning to choose the best parameters to make it work better for this special case of use, because an algorithm can be used in any problem, theoretically any problem, but it have to be set up for a special use with the proper parameter setup.
Okay, sounds good. Thank you.